This video is for the GCSE Astronomy Topic 6 Celestial Observation. This is a big topic. Just have a look at this specification. It's filled 3 columns. There's a lot in this topic, so I expect this is going to be quite a long one. But it starts just with us identifying certain bodies that you can see with the naked eye and a few you can't. Then we move on to navigation and different coordinate systems, and then we finish with some general tips about observation. And I suppose it starts simple. That's the sun. It's a very easy body to identify in the sky during the day, a little bit more tricky to identify at night. Then that's the moon. Probably know that by now. These are stars, although they probably don't quite look like this when you observe them with the naked eye. But there's something interesting about this picture. You'll see some of the stars are blue, and some of the stars are a yellowy colour, and some of them are a much deeper red colour. And we'll come to why that is a bit later. And then there are double stars. Now, double stars are stars that appear to be very, very close together in the sky. The angular separation between them is very, very small. And for naked eye observations, probably not going to be able to tell that there's actually 2 stars there. They're not necessarily close together. It could be that the 2 stars just happen to look close together, but one is a long way away, much further from the Earth than the other. They just happen to line up. So those are sometimes called optical double stars or visual double stars. But stars that are gravitationally bound to each other, they're close enough together to be bound to each other, are called binary stars. Now, usually they're so close together, with the naked eye you won't be able to see them. But if you can call them visual binary stars. And for the most part, the stars don't seem to move very much from day to day. I mean, they move throughout the day, but their relative position stays the same. So we came up with a system of breaking the sky into different chunks, different areas, so that we can address where different stars are and give them sensible names. The system we use is the system of constellations. There are currently 88 constellations. That's the official number that we're using. But constellations are often misunderstood. The constellation isn't the stars. The constellation is the area in the sky where the stars are. So this constellation of Aquila is identified by this blue dotted outline. Everything inside there is in the constellation of Aquila. The etymology of the word constellation, con means with, and stellar is star. So they're just stars that happen to hang around together. But they're often confused or mistaken for asterisms. Asterisms are these shapes that people have historically made by connecting the dots, a dot to dot of the stars. And this one here is the Plough, which in the United States tends to be called the Big Dipper, which is an asterism within the constellation Ursa Major. And you'll notice that these stars have a letter next to them, a Greek letter next, and that signifies the brightest star. Alpha is the brightest star, and it increases as it goes through the Greek decreases in brightness as we go through the Greek alphabet. So beta is a little bit less bright than alpha, and so on. Although sometimes they're so similar you can't really tell. With some variable stars, they can actually switch places, but the names are stuck. We'll talk more about that system later this video. Now there are clusters of stars as well, different types of star clusters. So here's an open cluster. This is the Pleiades star cluster. You can see this with the naked eye. It's very, very small, but you can see that there's something interesting. It's not just a few stars, there's a bit of a haze around it as well. It's called an open star cluster because there's no real shape to it. Unlike a globular cluster, which is more, well, the word globular, like a globe, it's more spherical in its appearance. And these can look a lot just like normal stars until you look really closely and you see they're a bit hazy around the edge and you realise that perhaps that's a globular cluster, not a star you're looking at. And there are even galaxies that you can see with the naked eye. For example, you can see Andromeda with the naked eye, but it's quite difficult to make out. And certainly you can't see all of the stars, just the very, very bright middle of Andromeda. So you can see some galaxies, but there are different shapes of galaxies. There are elliptical galaxies, and there are spiral galaxies, and you won't see something as beautiful as this with the naked eye. And there are barred spiral galaxies, and we'll go into all of these in more detail in a later session. There are ring galaxies, absolutely fascinating how they form. There are galaxies that don't seem to have any real shape to them. interacting galaxies, where galaxies are in the process of colliding with each other. But then, of course, the galaxy that you might be able to see with the naked eye is our galaxy, the Milky Way, which is a spiral galaxy. The word galaxy itself means Milky Way. Gala and xi means Milky Way. Now, the reason why the Milky Way looks like this in the night sky, if you ever get to see it, it's amazing to see, but you have to have a very dark sky to be able to see it. And it's usually better to look at it from the southern hemisphere. But the reason why the Milky Way looks like this is because we are in the Milky Way. We are part of this disk of stars in the Milky Way. So from within this disk, we're looking at the bulge in the middle of the Milky Way here. And there are some other things you can see with the naked eye. You can see nebula. Nebulae look a little bit wispy around the edges, nebulous. They're very, very difficult to make out with the naked eye. You can see far more interesting things, I think, in the southern hemisphere. But if you look at the Orion constellation, you can see some nebulae inside that constellation with the naked eye. Some nebulae seem to have some sort of shape to them. They're called planetary nebula. They don't have anything to do with planets, except that there's some sort of angular size to them. So when they were first observed, they were nebulous, and yet they seem to look a little bit like planets in the fact they had some angular size. So they get referred to as planetary nebulae, but they're not actually anything to do with planets. There are nebulae that they don't really have any shape to them. They're a bit more diffuse, spread out. And so here you can see, again, different coloured stars within this nebula. There's an orange one here, which is perhaps a bit older than this blue star here, which is perhaps a bit younger. The red colour you see within the nebula is probably caused by excitation of hydrogen by other stars nearby. Those stars nearby are emitting radiation, which excites the hydrogen gas within that nebula. That's what a nebula is. It's a cloud of gas and dust. And then there are nebulae that look really mysterious. They're spookily named dark nebula. Well, what you're seeing here is dust obstructing light from behind. So it's a nebula, but it doesn't have the gas that gets excited. And you can tell that because when you have a look at these stars, they're a bit fainter and they're all this very distinctive darker red colour. And that's because the light from those stars has been absorbed by this dark nebula that's between those stars and us. We can see planets, but with the naked eye, they don't look like this. You can see the Earth very easily from the Earth, just look down. But if you want to see other planets, they tend to look more like stars with a bit more angular size than other stars have. And of course, they don't twinkle. So this is a slide I showed in an earlier video, and there are certain points of light here that don't seem to be twinkling and certain points that are twinkling. And the points that are not twinkling, well, they probably planets. At a first glance, we might think they're planets. And the ones that are twinkling, well, they're stars. And it's because of the angular size of the body, so how big it appears in the night sky, and the turbulence, the air turbulence around it. A very small point of light, a little bit of air turbulence, means that it appears to come from slightly different directions. A much larger source of light, reflecting light from the sun, like the planet, maybe Jupiter or Venus that we can see, then there might be a bit of shimmering around the edge, not really going to notice it. Pictures like this you can take with some pretty good amateur telescopes, and you can get some fantastic pictures with some methods that we'll cover in a later session. But this is about naked eye astronomy at the moment, so things that you can see without a telescope. Here's a comet, I believe this is Hale-Bopp, which when I was a child was in the sky for, it felt like a year. You could look up and you could see it at some points. You could even see it during the daytime. It was so bright, this comet. If you look really closely, you'll see there's two tails coming off this comet that you can see quite clearly. We'll cover comets in a later session, of course. Very rare that a comet as beautiful as this appears. Usually you might see it as a small green wispy thing. They do tend to appear green when you look at meteors. Covered that in an earlier session, the difference between a meteor, a meteorite and a meteoroid. But as the meteor enters the atmosphere, meteoroid, it would look a bit like this. You'd see a bright flash. And of course you'll struggle to see a meteor when it's not entering the atmosphere. The aurorae, for example, the aurora borealis or the aurora australis, this is what they might look like. I've never seen them myself, but I really would love to see them. These are caused by charged particles from the sun entering the atmosphere and exciting the atmosphere as they do. And of course we'll cover aurora point. But this is what they look like. If you see a ribbon of colour in the sky, you might get lucky. You can sometimes see the aurora borealis from the United A supernova is an interesting one because you won't necessarily know that's what you're looking at. A supernova, super, usual meaning of the word super, but nova means new. So this is a star that's very, very bright, super, it's above all the other stars, and yet it's new. It wasn't there before. And you'd usually notice that if you get to know the sky very, very well and you suddenly see there's a star there that wasn't before, maybe it's a supernova, you might have made a great discovery. But usually you would compare pictures. But this is about naked eye astronomy, so the likelihood is you're going to struggle to identify a supernova with the naked eye unless you really get to know that celestial sphere. The key thing about supernovae is how bright they are. So here's a galaxy, and down here somewhere is some unassuming star that has gone supernova, and it's outshining the galaxy. It's so bright. A galaxy of billions of stars, and yet that one star can outshine them all because of the amount of energy released in that supernova explosion. Another thing you might see is an artificial satellite. So here is a particular satellite. This is one of the Iridium satellites, which produces, it's a very reflective satellite. It's got a very high albedo, is the technical word, a very reflective satellite. And as it passes around the Earth, it can catch the sun, and you can see a very bright flare. And this is what it might look like in the night sky. And you can get apps on your phone that will tell you where to look and at what time to see these iridium flares. They tend to happen quite fast. The International Space Station appears to move over a little bit slower, but here's a long exposure photograph of the International Space Station. The key thing with a space station, I suppose it's a type of satellite, is that it's moving in a straight line, and it'll appear as a very fine dot just moving in a straight line, but it won't appear to be moving too fast. A bit faster perhaps than a plane, but it's not shooting across like an iridium flare looks like it's. And then of course there's aircraft. So you can just about, if you squint, you might just about see that there is an airplane here. And the distinctive feature of aircraft, when they're flying at night, is they've got lights flashing. So if you see lights flashing, probably not a satellite, probably an aircraft. But it can be difficult, especially when the aircraft are very, very high up, cruising at 30,000 feet or whatever. I'm not a pilot. But it can be quite difficult to decide whether you're looking at an airplane or at a satellite. And usually it's the speed. If it's that high up, it wouldn't appear to be moving very fast, whereas a satellite then would appear to be going a bit faster. But if the plane's a bit lower down, the plane will appear to be moving faster than the satellite. There's a lovely picture here that shows the three different things you can see. So a meteor here, the trail from the meteor, it tapers. It starts quite thin, it gets thicker, and then it gets thinner towards the end again. Whereas a satellite doesn't really do that. It's just one thin, the brightness doesn't change very much as the satellite goes across the sky. The plane trail, well, that's flashing. You can see that. Now, there are certain constellations that you have to be able to recognise, and you have to be able to reproduce, draw. And so Cassiopeia, I think, personally my favourite constellation. This is a very distinctive one, very easy to spot in the night sky. Once you know what you're looking for, you can find it with relative ease. You just look up and say, oh yes, look, there's Cassiopeia, and amaze your friends. It looks a bit like a W or an M, depending on what time of year you're looking at it. And these 5 stars, very, very bright compared to the stars around them. Another very easy to identify constellation is Orion. Usually people go straight for Orion's belt. These 3 stars here are quite easy to identify. And this part down here, this Orion's sword, there's some really interesting things you can see if you look with a telescope in that area of the sky. Orion Nebula, things like that. But if you look up here, there's some more interesting features that you might be able to see. So if you were asked to sketch Orion, you'd certainly need those 3 stars there, then the 2 stars here and the 2 stars here producing this sort of egg timer shape, and then pop another one up here for the head and figure the rest out from that. This is the general shape of the asterism within the Orion constellation. And this one here, as I said, in the UK it gets called the Plough. In the United States it tends to get called the Big Dipper. I'm going to call it the Plough. But this is, again, a very distinctive shape and a very, very useful asterism for navigation. You can use this to find other stars. You can use this as a waypoint, point to other stars. And Cygnus is another quite easy to identify constellation, although I tend to struggle to identify the edges of Cygnus when I'm glancing up at the night sky. But this cross here is quite easy to spot. because the stars along that cross are quite bright. Cygnus means the swan, and this is supposed to look like a swan. Now, according to the specification, you also have to be able to identify the summer triangle, which overlaps with this asterism, or both of those asterisms are within Cygnus. So here it is. I've never really been able to say, well, that's the summer triangle, and I've never found it particularly useful to do so. But if you're following a guidebook that says identify the summer triangle, then follow from this star, well, this is what it is. And what I think is the second hardest asterism for me to see in the night sky is this great Square of Pegasus. Here it's just labelled Square of Pegasus, but the great Square of Pegasus, I really struggled to identify. I find Cygnus and I look at the sky and I think, is that the square? The stars aren't especially bright compared to the stars around them, so I find that one a bit of a challenge. This will help you hopefully identify the Square of Pegasus next time you're out doing some stargazing. But by far the hardest one to observe in the northern hemisphere is this one, because you can't see it. This is in the southern hemisphere, and where this crosses is very close to the south celestial pole. So those were the bodies, the objects that you would have to identify and perhaps be able to sketch. So let's look at how we can use these asterisms for navigation of the celestial sphere to identify other stars. And the first example we've got here, the one that everyone first learns, is how to find Polaris from the Plough. So here's the Plough, and if you look at this part of the Plough here and follow those stars along, the next star that's reasonably bright, it's not the brightest star in the sky by far, but the next one that's reasonably bright is Polaris. And you can also find Arcturus by following the other side of the Plough. And you have to kind of follow it round. Where this curves, you follow the curve around, and then you'll find Arcturus. Polaris is quite straightforward to find. Arcturus, perhaps not so much. But this is the sort of diagram you need to be able to reproduce. So 3 more bodies to look for in the night sky. There's Pleiades, there's Aldebaran here, and there's Sirius here. Sirius is the brightest star that you can see in the night sky. So you start from Orion, and then you look at Orion's belt. There's Orion's belt, and you can follow the line of Orion's belt in 2 different directions. If you want to find Sirius, you follow this part that on this diagram is to the right, but in that direction, following down from the end of the belt, and you'll see Sirius just down there. A very bright star. If you follow in the other direction, then you'll go just past Aldebaran, and if you carry on, you'll reach the Pleiades. And they're quite easy to recognise because there's an open cluster of stars. So if you find Pleiades, you've gone past Aldebaran. Next up is what I think is the hardest one to identify, the way that the GCSE Astronomy wants you to identify it. I think there's an easier way which I'll show you. And that's using the Great Square of Pegasus. And you can see why I find the Great Square of Pegasus so hard to identify. If you look at the little animation on the bottom left, those 4 stars in the corners are quite unassuming. But this one here, if you look closely, is a little bit more red than the other 3. That means that when you look at that star, you can use that as a reference point. When you look up at the Great Square, you say, that one's a bit more red, let's use that as our reference. And then if you work anti-clockwise in the northern hemisphere, anti-clockwise around from this red star to the next one around the Great Square, that's a starting point for trying to identify the Andromeda galaxy. So the next step to take is to count to the next star in the asterism over here, which is part of the Andromeda constellation. Not the Pegasus, this is part of Andromeda constellation. So you count 1, 2 stars around on the 2 arms that come around for Andromeda, and then you count 1, 2, 3. So the distance to Andromeda galaxy is about the same as the distance between these 2 stars, and it's in that same direction. So here's a magnified picture. Here's that red star, anti-clockwise round from that red star, 1, 2, and then follow it along to get to Andromeda. Incidentally, that red star is called Shat, or Beta Pegasi. I prefer to pronounce it Beta Pegasi. So that's the way the exam board expects you to remember how to find the Andromeda galaxy. Following from Shat, going anti-clockwise to the next star within the Great Square of Pegasus, and following around these arms, which are part of the Andromeda constellation, and then across to Andromeda. The way I find that's easier is to actually start from Cassiopeia and ignore the Great Square of Pegasus altogether and start from Cassiopeia. So Andromeda is here. Here's Cassiopeia, very, very easy to identify in the night sky. And if you follow a line from the sharp point of Cassiopeia all the way down, Andromeda is just a little bit round in a direction opposite from the shallow. So you just look down, then think it's a little bit further round than that, and you can sort of make it out. You get used to these sorts of relative distances, the angular distances in the sky. You get used to looking for, and I find that far easier way to find Andromeda. You can also find Fomalhaut from the Great Square of Pegasus. So I've kept the Great Square of Pegasus the same orientation here. Fomalhaut is down here, and here is that red star we talked about earlier. This time we go clockwise and then follow that straight line down. It's quite a long way. Fomalhaut is just above the horizon when you're in the northern hemisphere. And I mentioned, of course, the Big Dipper and the Plough, the fact that we've got different names in the United States and the United Kingdom. But if you go back into history, there are all sorts of different names for these asterisms. The thing is, we needed some way of remembering the asterisms, and we needed some way of referring to them and teaching them to our children and so on. And these asterisms were so useful for navigation that different cultures independently developed their own systems for naming these constellations and these asterisms. Obviously, these names had to be names that the cultures could remember, so they had to be culturally identifiable names. And that's why there are historically different names for these asterisms. The stars that can be easily seen in the night sky and are useful for navigation tend to have their own special name. For example, Fomalhaut. But there are stars that don't seem to have a special name, or at least the special name gets forgotten about. And there we use a different naming system. So what Johann Bayer did is he named the star based on the constellation where it is and how bright it is, starting from Alpha, working your way down. So Alpha Cassiopeiae was the brightest star in Cassiopeia. Beta Cassiopeiae was the second brightest star in Cassiopeia, and so on. So there's the Greek alphabet. If you want to get that down, that's the scheme that we use. On star maps, you'll notice sometimes that they're drawn where some of the stars have a larger diameter than others. And that's how star maps try to indicate the brightest stars. The larger the size of the spot, the brighter the star. We're going to move on now to coordinate system. And that's how we can record where in the celestial sphere an object appears to be. There are a few coordinate systems. So we're going to start by looking at the celestial sphere. And we have a north celestial pole, which is directly above the north geographic pole, and a south celestial pole, which is directly above the south geographic pole. And the point is that the geographic coordinates have an equivalent on the celestial sphere, which is this imaginary sphere that's some distance away from the Earth. The Earth sits inside it, and you can imagine all the stars are sat on that sphere. It's not quite how it is, but it's a way of addressing a position within what we can see in the sky. So we also have a geographic equator, that's the equator on the Earth. Therefore, we have a celestial equator, an imaginary line on that celestial sphere that is always directly above the geographic equator. And there is a coordinate system which is based around that celestial sphere where we use the celestial equator. It's called the equatorial coordinate system. Now you're used to latitude and longitude. Well, here we've got declination and right ascension. Latitude is a geographic coordinate, how far north and south you are, which corresponds to declination, which is a celestial coordinate. Longitude is a geographic coordinate, how far east and west from the prime meridian you are, and there is a celestial equivalent, right ascension. Just like with latitude and longitude, those coordinates can be given as angles. It's the same with declination and right ascension. Just like with latitude, where it's positive as you go north, negative as you go south, it's positive as you go to the northern celestial sphere, the declination, and the declination is negative when you go to the southern celestial sphere. Now, in the northern hemisphere, when you look up at the celestial sphere, right ascension increases as you look from right to left. But just like with the geographic coordinate system, we needed a prime meridian, which runs through Greenwich. There's also a celestial prime meridian. A meridian is the name for any of these lines that passes through the North Pole, through the South Pole, and directly over someplace on Earth. So that's a celestial meridian. They're the celestial equivalent to the geographic meridians, which are those lines that connect the North Pole to the South Pole, passing through some place on Earth. So our celestial prime meridian is the first point of Aries. And we've covered this in an earlier video, but I'll just put it here again, just in case you want a refresher. In the vernal equinox, that's where the Sun is relative to the Earth. It's over there at the first point of Aries. So that is our 0 degrees right ascension. And as we look from right to left in the northern hemisphere, left to right in the southern hemisphere, we increase the angle from 0. The angle isn't always given as an angle. It can actually be given as a time. So starting from 0 hours right ascension, from right to left, as I say, when you view from the northern hemisphere, you can increase all the way up to one full rotation of the Earth, which doesn't quite take 24 hours. It's 23 hours and 56 minutes. But you can give your right ascension in hours and minutes, or you can give it as an angle. So how do we use this celestial coordinate system to identify the location of an object in space on the celestial sphere? So what you would do is you'd start from the first point of Aries, and then you would look at your right ascension and your declination, and use that to identify the position of your body. So here is the celestial sphere. Here's some star sat at some point on the celestial sphere. Here is the first point of Aries, and we read around our right ascension. We often use the letter alpha for this when we use equations. And alpha goes around the celestial equator, which remember is directly above the geographic equator. And maybe that's 90 degrees, 30 degrees, it doesn't matter. Maybe it's given as a time, 3 hours, 6 hours, it doesn't matter. And then there's the declination, which is how far to the north, or how close, how much you have to look up towards the northern celestial pole. Or if you're in the southern hemisphere, it's negative declination, it's the angle towards the south celestial pole. And for the sake of this, you can ignore the ecliptic pole and the galactic pole, although you could probably work out what they mean, but don't worry if you... So there's an alternative coordinate system, and the alternative coordinate system is the horizontal coordinate system. Now here we use what we can see from our point on the Earth's surface. We are an observer on the Earth's surface, and we can get our compass out, we can tell where north is, and we use the same sort of system where we have an angle around from the north towards the east, but that's not our right ascension, that's our azimuth, and then we have an angle up from the horizon, which here is listed as altitude. It's sometimes called altitude. We prefer to call it elevation. So you have an azimuth and an elevation. And any point on the celestial sphere can have a coordinate that has an azimuth and an altitude, or an elevation. But you can see the problem with this is that the Earth is rotating. So the coordinates using the horizontal coordinate system for a particular body in the celestial sphere will change over time, but they won't change over time for the equatorial coordinate system. The other issue is, of course, if you're in different places on the Earth's surface, then you're going to get different coordinates, whereas that doesn't happen with the equatorial coordinate system. In this diagram, you can see the celestial meridian, which connects the North Pole to the South Pole and passes through the very highest point in the sky, which is called the zenith. The opposite of that at the bottom is called the nadir. But from the North Pole to the South Pole, from the North Celestial Pole to the South Celestial Pole, an imaginary line that passes right overhead, that's your meridian. So some key coordinates that is worth remembering. The celestial equator, declination is fixed at 0 degrees. If you go north, the celestial North Pole is fixed at positive 90 degrees, and we include the plus sign there. The South Celestial Pole, declination of minus 90 degrees. And then we can see these here. The horizon has an elevation of 0 degrees. That's on the horizontal coordinate system. That's 0 degrees. The zenith directly above us is 90 degrees, and the nadir directly below us is minus 90 degrees. And again, we'd use our pluses and minuses here. And the tricky bit is to transform the coordinates that you can see in a book that tells you the equatorial coordinates of a body to your horizontal coordinates, so you can either choose where to look in the sky with maybe binoculars or a telescope, or if you're doing naked eye astronomy, you just know where to look in the sky for a particular body. So I'm just going to go through 4 examples so we can form some rules of how to convert from one coordinate system to another. And we're just going to look at declination, and we're going to look at elevation. We'll worry about right ascension later. So if we're stood on the North Pole, We have a latitude of 90 degrees north, positive 90 degrees, the geographic North Pole, then the North Celestial Pole is directly above us, so that means it has a declination of 90 degrees. Remember, the zenith is 90 degrees. So for that example, it looks like you'll think, well, the elevation is the same as the declination. Well, not so fast, because if we're standing on the equator, then the North Celestial Pole, which has a declination of positive 90 degrees, is directly above the geographic North Pole. That's where the celestial North Pole is. The elevation is only 0 degrees. It's right on the horizon. If we look at this picture here, it will make it a little bit clearer in your mind. If you're stood right at the top here of the Earth, then right above you is the North Celestial Pole. But if you stood here on the equator, then the North Celestial Pole is right here. It's right on the horizon. 0 degree elevation. So what if we're standing in England, and I had to pick a place in England, so I picked London, sorry. But if we pick London, we say we're at a latitude of 52 degrees, that's 52 degrees north, then the North Pole celestial North Pole has a declination of plus 90 degrees, it still does. Well, now the elevation is just 38 degrees. So you might be looking at these numbers and starting to form a rule in your head. Maybe you're looking at 52 and 38 and thinking, well, how can I combine them to make 90, maybe? So let's look at another example. Let's look for Polaris. Now, Polaris is almost on the North Celestial Pole. It's just 1 degree out. So if we're standing at a latitude of 90 degrees north, Polaris has a declination of 89 degrees. And the elevation is going to be 89 degrees. That makes sense. If we stood on the equator, 0 degree latitude, remember Polaris has a declination of 89 degrees, the elevation, it says here at the celestial meridian, so that's the maximum elevation, it's just 1 degree. It just gets 1 degree above the horizon. That's the maximum elevation, which is the elevation as it crosses the celestial meridian, what we call culmination. We'll come on to that later. The third bullet point here, it says, well, what if we're standing in London? So if we're standing in London, 52 degrees north, Polaris is 89 degree declination. The elevation of it this time is 53 degrees. So check your rule that you came up with for the last example. Does it work for this example? If not, maybe the rule is wrong. And the key thing here is, when I'm standing in London, or anywhere in the Northern Hemisphere, and I look at the North Celestial Pole, Polaris, which is going to be moving around it throughout the day, will be a degree higher, or a degree lower, but a degree higher when it's at the highest point. So 2 more examples. Let's just pick 2 more stars. Sirius A, which is the brightest star in the night sky. Let's imagine we're standing on the geographic North Pole. Sirius A has a declination of minus 17 degrees. That means we will not see it. That means its elevation is minus 17 degrees. It's below the horizon by 17 degrees. But if we're stood on the equator, the geographic equator, Sirius A, with its declination of minus 17 degrees, has an elevation, much higher elevation, of 73 degrees. That's when it's at its highest point, as it crosses the celestial meridian. So what if we stood in London? Well, if we stood in London, we can see Sirius A. It has a declination of minus 17 degrees, and we are 52 degrees north. So the elevation of Sirius A, as it passes the celestial meridian, when it's at the highest point in the sky, is 21 degrees. So how do you work these out? You use these formulas at the bottom of the screen here. Your elevation at the celestial meridian of the body you're looking at is going to be 90 degrees, either plus the latitude minus the declination, or minus the latitude plus the declination. The latitude here refers to the observer's latitude. The declination refers to the angle above the horizon for the highest point that the body will reach when it crosses the celestial meridian. And the reason why you've got 2 here is because the body in 24 hours, well, 23 hours and 56 minutes, is going to complete 1 circle. So it's going to cross through your celestial meridian twice. The highest one is whichever one is less than 90 degrees. If it's more than 90 degrees, it's gone too far the other way, you wouldn't see it. So here's the last example for you then. We've got Deneb. We are in Madagascar, so we're in the southern hemisphere this time. Deneb has a declination of 45 degrees. So you plug it into this equation, 90 degrees plus our latitude which is minus 19, use minus if it's south, minus our declination of Deneb, which is 45 degrees. And is that less than or greater than 90 degrees? So if it's greater than 90 degrees, then we'll go 90 minus the latitude, which is minus 19, so that's 90 plus 19, and then plus the declination, which for Deneb is 45 degrees. Is that more or less than 90 degrees? So in this example, we'll use the top equation. So here's a question then. And you can pause this video if you want to try this question yourself. But here's a quick question for you. The elevation of the celestial meridian, or the elevation at the celestial meridian, so that's the highest elevation of Fomalhaut. Fomalhaut has a declination of, and I've given the angle in a horrible way, minus 29 degrees, 57 minutes, or arc minutes, and 20 arc seconds. We're standing in Chad, in Africa, with a latitude of 15.45 degrees north. And what I would like to know is, what is the elevation? So pause the video if you want to try and work it out. And so the first thing we need to do is get that declination into degrees. So let's get the arc seconds into arc minutes by dividing through by 60. Then we get those arc minutes, about a third of an arc minute, and add it to the 37 arc minutes that we've got in the original number to get 37 and a third arc minutes. Then we turn our arc minutes into degrees by dividing by 60, and that gives us about 0.62 degrees. Then we add the minus 29 degrees, so we add 29 degrees to 0.62 degrees to get 29.62 degrees, but the whole thing is negative. So our elevation at the celestial meridian, we plug our numbers into the equation, we get our answer. We use the top equation this time because it gives us an answer below 90 degrees, 75.83 degrees. Now, you can use observations of celestial bodies to find what your latitude is, so how far north and south you are. And you can see here the declination of Polaris is about 89 degrees, but if we call it 90 degrees, it's almost 90 degrees. Our answer will be 1 degree out. If it's almost 90 degrees, then the latitude is about equal to the elevation of Polaris. So if you can see Polaris in the northern hemisphere and you can somehow measure the elevation to Polaris, then you know your latitude. Very, very helpful for navigation. So here I've got a little diagram for you. You can see the North Pole here. This is the geographic North Pole. So above it is the North Celestial Pole. And the light from Polaris is coming straight down. So far away, all the light is going in a straight line from. And we're some observer stood here on the surface of the Earth. We would observe Polaris to be that high above the horizon. This line here, the tangent to the circle, is the horizon. So we measure our angle above the horizon for Polaris. It turns out that's the same as our latitude. And if you want some sort of confirmation of that, try and visualize this picture and imagine that you were stood further and further and further north. And as you do that, this angle will increase, but so will this angle. And eventually this angle will be 90 degrees, and so will this angle. And if we were stood on the equator, this angle would be 0, and so would this angle. So you can see the two angles are the same. You can use a device like this, which you can make yourself, to measure these angles. What I've got here is a protractor, a very narrow tube. You could put a crosshair across the tube if you want with some string or something. You've got a narrow tube, and from the middle of the protractor, not from the edge of the tube, from the middle of the protractor, I've suspended some string with some weight on the end. Just stuck a nut on the end of this one, and the nut will always hang down. So you look through the tube, and then you get a friend to read off from the protractor after the nut has stopped swinging what the elevation is to that, sometimes called altitude, to that body you're looking at. There's a more sophisticated version of this, which is called a sextant. And a sextant works in a very similar sort of way, except you haven't got to rely on gravity. You line up with the horizon, you clamp in place what the horizon is, and then you look at the horizon while simultaneously moving a different part, so you get the two images together, and then you can read the angle between the horizon and the body you're looking at. This is very useful if you're on a boat bobbing up and down, because the pendulum's going to keep swinging, but you can keep your sextant pointing at the horizon. You can adjust your hand accordingly. So, just a reminder, prime meridian is the Greenwich meridian. The longitude can be given as an angle, as you can see here, but it could also be given as a time. And it can be given as a time because there are 24 hours in a solar day, a mean solar day, and so we can divide our Earth into 24 slices. And we could say that you have a 1 hour longitude, a 2 hour longitude, and so on. Well, it turns out you can do the same thing with the celestial meridian. So the celestial meridian, remember, is an imaginary line that connects the south celestial pole to the north celestial pole and passes through the zenith, and that's represented by this protractor here. And the celestial north pole is in this direction over here somewhere, and that line goes all the way around the Earth. That's the meridian. And this line here is perpendicular. It's a plane perpendicular to that plane of the meridian. It's 90 degrees. So that's your celestial equator. And you can measure an angle around from the celestial equator as a time. It's called an hour angle. So the body will rise in the east, well, it's like the way the sun rises in the east and sets in the west. A star might rise in the east and set in the west. And if it's over here somewhere, the body has already passed the celestial meridian. You can measure this angle, how far past the celestial meridian it is, to know how long ago it passed the celestial meridian. So I've got here 24 hours equals 360 degrees. It's not quite right, is it? 24 hours is a mean solar day, but a mean sidereal day is 23 hours and 56 minutes is equal to 360 degrees. For these sorts of questions, you can get away with 24 hours. So by convention, we say a time or an angle which is positive is a westward angle, like you can see here. Negative would be an eastward angle. So a nice way to think about it is the hour angle is the time since it passed the meridian, since the body passed the meridian. So if it's negative, the time since it passed is negative because it hasn't actually passed it yet. So that's quite a helpful way of thinking about it. Now I have to introduce a new concept to you called sidereal time, local sidereal time. There's a sort of a sidereal noon when the first point of Aries is directly over your meridian, or when your meridian is the prime meridian. That's when it's the first, when the Earth's rotated around so that you're in that position, then you are in your local sidereal noon. As the Earth continues to rotate, you add hours on. But you have to be careful, because you don't add 24 hours in a mean sidereal day. You add 23 hours and 56 minutes in a mean sidereal day. That's what's equal to one full rotation, which is 360 degrees. So you can see here the definition of a new term, right ascension, which is the angle from the first point of Aries around to the point that you are looking at, the point in the celestial sphere, the object that you're interested in looking at. So if you're viewing from the North Pole, the North Celestial Pole down at the Earth, then this is an angle measured anti-clockwise from the first point of Aries. And the angle can be given as a time, or it can be given in degrees. So let's imagine that you are stood here, this red dot here, which apparently is New York. This is your observer. Your local mean solar time can be calculated here. It's this angle here expressed as a time, where 360 degrees is 23 hours and 56 minutes. And the local hour angle, which here is this cyan-coloured arrow pointing around here, LHA, the local hour angle, is just going to be the local sidereal time, which is this magenta arrow, minus the object's right ascension. You might want to pause the video and really study that diagram a bit and the equations at the bottom to get your head around how to convert from a local hour angle and a local sidereal time to an object's right ascension, or any of those sorts of conversions. What it means is that you can use this to tell the time, because if you know an object's right ascension, you get a big book and you look up the right ascension for the object. So you've got this value here, and then you look at the sky and you get your various instruments for measuring angles, and you measure the hour angle for that body. Or maybe you time how long it's been since it crossed the meridian, so you've got an hour angle for it or something. If you've got an hour angle for it, you can now calculate your local sidereal time. The last step is to convert your local sidereal time into a mean time. Big book of tables would be the easiest way. You don't need to worry about that for your GCSE. But if you look at the last line here, you can see it. Greenwich sidereal time, not the same as the solar time, equals observer's longitude, plus the observer's longitude minus the object's right ascension. So you can do the conversion this way. So you can use this to find out what the Greenwich sidereal time is. It'll be quite useful for navigation again. Because if you know your local sidereal time and you know the Greenwich sidereal time, you can work out where you are. So here's some definitions. So hopefully this is going to help clear some of this up. And I'm not just going to read these to you. If you're interested, you can read those yourself. Maybe pause the video whilst you read it. But what's frustrating is that some of these angles are measured clockwise and some of these angles are measured anti-clock. So make a real mental note, or even a on paper note, of what the different angles are. I'm just going to tell you what the abbreviations are for these different definitions on the diagram down there. So Greenwich sidereal time, we're going to use mean. So that's the Greenwich mean sidereal time is GMST. Local sidereal time, again, we're going to use the mean sidereal time because we know it does vary a little bit. So that's LMST. Greenwich hour angle, GHA. Local hour angle, LHA. And right ascension is just listed as right ascension. And over here is the first point of Aries. This is a body that you might be interested in looking at. And here we are, stood in New York. This point over here is the Greenwich meridian. That's where Greenwich is. London is right there. It's a lot to digest, so do take your time with that. Now, cardinal points in geography refers to your north, south, east, west, but there are other cardinal points in astronomy. For example, the zenith, the nadir, and you've got your north celestial pole, your south celestial pole, and you've got things like the celestial equator. These are all key cardinal directions that you should be aware of. When we refer to diurnal motion, what we're talking about is the motion across a day. So if you look here, you can see across 24 hours, 23 hours and 56 minutes, the celestial sphere appears to rotate relative to the surface of the Earth. Of course, we actually know the Earth is rotating within the celestial sphere, but this is the way it appears to an observer. You'll get a full 23 hours and 56 minutes for a body to make one full rotation. Now, when a body crosses the meridian, there's a technical word for that, which is culmination. Sometimes that word is used incorrectly in the media. For example, recently, Jupiter and Saturn were both very, very close together and they culminated. They both crossed the same meridian, but then people thought that just meant they were close together. So the meridian there, we've already talked about several times. The zenith we've talked about, but a new word here is circumpolar. A circumpolar star is one where, from where you are, from the observer's position, across the 23 hours and 56 minutes, the star never dips below the horizon. It never has an elevation that is negative. And you can see, some nice pictures like this, long exposure photographs. The north celestial pole will be right in the middle here. And if a star goes all the way around, it's circumpolar. And if it doesn't, it isn't. If it dips below the horizon, it's not circumpolar. Ignore the buildings. It's the horizon that we care about. A very simple rule for this: if the angle from the celestial pole is less than the latitude, the angle from the celestial pole, then the star is circumpolar. And the angle from the celestial pole is not the same thing as the elevation, so you've got to be careful. Here's the celestial pole in the middle. The angle from the celestial pole is measured out from it. That's also called 90 degrees minus the declination. 90 degrees minus the declination is the angle from the celestial pole. That's going to be less than or equal to the latitude for stars that are circumpolar. And there are two transits. I mentioned this before. There are two transits. A star will cross the meridian twice, and so stars have an upper transit and a lower transit. And the upper transit is when it's at the highest point in the sky. The lower transit is when it's either at the lowest point in the sky, or it might even be, in the case of non-circumpolar stars, below the horizon. So you see this diagram here. We're viewing from the side. Here's the meridian, and the meridian on this diagram is straight overhead. So here we're looking towards the north celestial pole, and here we're looking towards the west. And you've got your upper transit and your lower transit. They're both examples of culmination. So some stars, which are not circumpolar, they appear to rise and then set, rising and setting stars. And they move around that arc 15 degrees every hour, roughly, because there are 23 hours and 56 minutes in a full 360 degrees. So it's roughly 15 degrees of angle. And the stars move anti-clockwise in the northern hemisphere. In the southern hemisphere, they appear in the northern hemisphere anti-clockwise around the north celestial pole. This is quite handy to know for deciding when to do observations. So I used a piece of software here, and you can use all sorts of software. There are apps you can get for your phone that you can use. Just search for any sort of astronomy app, various sky maps and that sort of thing, which you can use in order to explore the celestial sphere. So this particular piece of software, you can use it to draw sky maps. So here we've got Polaris, and down here we've got Mizar, although actually that's Mizar and Alcor. There's two stars very, very close to each other. It's a double star. And maybe you're interested in trying to see the double star. Now you know that Mizar and Alcor are a double star. You might be really interested in trying to see that with the naked eye. So you get outside at 6 o'clock and you have a look and you notice Polaris there, and you know Mizar's down here and it's too close to the horizon. It's shimmering too much. You can't see it very well. The elevation's just 16 degrees. So you think, well, I'm going to have to wait a bit. How long should I wait until Mizar is up here? Maybe I want Mizar to have an elevation of double this, 32 degrees. There's an elevation of 32 degrees. It'll be up here somewhere. But there's my circle that Mizar will trace around across the course of 23 hours and 56 minutes. I know it moves 15 degrees around that circle for every hour that I wait. Now, I can do some very clever geometry, which you don't need to know for your GCSE, to work out that I would have to wait. I can do some very clever geometry, which you don't really need to know for your GCSE, to work out that this angle here has to be just a bit more than somewhere between 67 and 68 degrees. That means I've got to wait until about 10:30 before I can see Mizar and Alcor nice and clearly, about 32 degrees elevation. So some of the best conditions for observing stars is when they are culminating, when they're at the highest point in the sky. And if a star isn't culminating yet, you can take a look at it, you can approximate the angle it has to move around, look at your watch and realise how long you'll have to wait until the star does culminate. If you're 15 degrees, it's going to be about an hour. Now, a lot of apps that you can download will allow you to fast forward time. So there's a little slider or something you can look at and you can say, I want to see that star, it's too close to the horizon, fast forward, that's how long I have to wait before I can see it. Really good apps to use. And knowing about the apps is actually part of your course. But even if you get a star nice and high in the sky, it doesn't necessarily mean you're going to be able to see it. And there's a few reasons for that. Obviously, light pollution, you've seen this one before, means you don't have the contrast you'd need to be able to see the star against the background of the sky. When I lived in Manchester for 11 years, the light pollution there was so atrocious. The sky was orange. It was unnerving that for months on end you'd look up and just see an orange sky. It did clear sometimes, but there are times in the year where the light scattered off that orange sky was brighter than the street lamps. The best time to do your observations is when you've got as little light pollution as possible. That means a new moon. That's when the moon is dark. That means you want a dark sky. So you don't want to do it during the summer. You're going to want to do your observations in the autumn, winter and spring. This is sort of the astronomy season, the observation season. And there are some great websites you can go to. I'm not endorsing this in a sense. I just found this by Googling it. But if you go to the Dark Sky Calendar, it will tell you the best times to do observations when the sky is darkest. Really good to look it up before you go out with your telescope or even doing some naked eye observations. So you want as large elevation as possible to get away from that horizon, so there's less air in between you and the body you're looking at, so there'll be less shimmering and shaking of the body. Close to the zenith as possible. And the closer it is, the clearer the observation. This bottom point here, you can work it out with clever geometry, or get an app. Go grab your app, get your software on your PC, look it up online, but the apps are good to use, and you can work out what time you need to go out to look at an object. Or if you think you see something interesting in the night sky, a lot of the apps on phones will have the phones have a sensor in them to detect their orientation and a GPS device to detect where they are, where the phone is on the Earth's surface. And so when you point it at a particular star, it can tell you what it is. Very, very clever. So other things to consider when doing observations. The time to observe something usually is exactly halfway between when a star, or whatever body you're looking at, rises and sets, because that's when it's going to be culminating. That's when it's going to be at the highest point in the sky. That's a nice quick rule. The only exception to that rule is if you've got a star which you wouldn't usually see at night, in the middle of the night, because they culminate during the day. And if that's the case, then you're going to want to be as late as you can that the sky is dark, but not so late that the body drops too close to the horizon. So there's a bit of trial and error here. You want to be 15, 20 degrees above the horizon, 15, 20 degree elevation, to be able to make good observations. But sometimes you'll see a planet, for example, which will, like Mercury, very early in the evening, it will dip below the horizon. And so you'll miss it. You won't be able to see it. Other things to consider, you need to be able to see the sky. If there are clouds, you can't see them. But it's not just that. Any sort of fog in the air is going to affect your visibility. And then there are things called seeing conditions. And seeing conditions are a bit more subtle. If there's a lot of wind, or if there's a big difference in wind speed at different altitudes, and when I say altitude, I don't mean elevation, I mean height above the Earth's surface, then stars are going to twinkle more. So there's big differences in temperature, then there's going to be lots of turbulence. And there was a scale that you can use when you're doing your observations to say how clear the seeing conditions were. And it's a good scale to know. It's perhaps a little bit archaic now, some of the language, perfect seeing without a quiver, but it works. And really, if you're in sort of seeing condition 5 down here, very bad seeing, scarcely allowing to make a rough sketch, wouldn't waste your time, you'll just be frustrated. Other things to consider: your landscape around you. So this is a place called the Astronomy Resource Centre in Essex. I've never been here, and I hope whoever owns this house doesn't mind me taking a picture of it. Or I didn't, Google did. But right here, you'll see there's a square of trees. Right in the middle of this square of trees, you can do some really good observations because the trees block out light from around the outside. So it's a good place to do some decent observations. You want to be far away from cities if you can help it. You want to be rural so there's less light pollution. And it says here trees, but hills and mountains, all that sort of thing, can block any light from coming in from the sides. But also, if you can get up a mountain, if you can get up a hill, there's less air between you and the object you're looking at. And that's why some of the best observatories are built up mountain. I'm not suggesting you traipse up Snowdon with a telescope, but you would see far more stars at the top of Snowdon than you would in the flat plains of Essex. So you're doing your observations, your naked eye observations, you get out there and you see 5 stars and you feel demoralized. Just wait. If you wait about half an hour, then you'll start seeing stars that you couldn't see when you first went out. The intensity of the stars that you can see, after a long time, you start seeing dimmer and dimmer and dimmer stars. And that's because your rods are far more sensitive to these low light conditions, but they do take about 30 minutes before then being bombarded with lots of light before you can... there are pigments within your rods and cones. When they're exposed to light, there are pigments in your rods and cones. And if you don't expose your rods and cones to light, those pigments regenerate. And it can take quite a time. It can take about 30 minutes, even up to an hour, before you've regenerated enough of these pigments to really be able to see some of those very faint objects. Now, dark adapted vision you can ruin in a second, in less than a second. A flash of white light, and all of a sudden you've got to replenish all those pigments again. They've all been used. So you've got to replenish them all. So if you're operating in the dark, what you're going to want to use is red light, because red light doesn't use up these pigments, so you don't have to wait for them to regenerate. And you can see from this, the rods are far more sensitive to low light levels than the cones are. Now, you tend to have a higher concentration of cones here, which is, there's a huge concentration of cones. That's where the light focuses when you're reading, for example. Really fine focused vision is here. Your peripheral vision around here at the edges, you have a higher density of rods. The rods are the more sensitive to low light levels. So if you want to see very, very faint stars, you have to train yourself to use your what's called averted vision. Rather than looking directly at what you want to look at, you look a few degrees to the side. And it's difficult to do. You have to train yourself to do it. But you look a few degrees to the side, that's where you focus. But your brain is trying to focus without moving your eye on the body you're interested in, which you can now see. And as soon as your eye goes boom and you look at the body that you were interested in, you can't see it anymore because now you've got a lower density of rods, a higher density of cones, and the cones aren't sensitive enough to pick up the light from it, so you can't see it anymore. So averted vision and dark adapted vision work together quite nicely. If you stay outside for about half an hour, don't use any white light, just use red light to illuminate what you want to look at. Tip here, if you're using a white piece of paper, don't take a red pen out with you to write with, because red light will mean you won't be able to see what you're writing. And you want to use your averted vision to see those really pale objects. Okay, we did it. That's the end of this topic 6. An awful lot crammed in there, an awful lot of very complicated and very technical ideas. You watch the video again, pause it, really concentrate, and you can get questions to practice these sorts of skills of coordinate transformations and such from the Edexcel website. Well, I do hope you found that useful, and well done for sticking through to the end. If you have not yet subscribed to my channel, then please can I encourage you to do so you get notifications when I release more of these astronomy videos. And if you know anyone else that's doing GCSE astronomy or GCSE physics or A-level physics, and you think they'll benefit from the tuition that I offer every week, then recommend Physics with Keith to them. Thank you very much.